Welcome to VPC Service Controls Mastery. Today we're diving deep into Google Cloud's most powerful security feature, VPC Service Controls. This isn't just another security tool. It's a complete paradigm shift in how we protect cloud data. Traditional cloud security relies primarily on identity and access management. Basically, if you have the right password, you can access everything. VPC Service Controls adds a crucial second layer by saying even with the right password, we're going to check where you're accessing from, what device you're using, and whether this access pattern makes sense. Think of it like this. Your house has a front door lock, that's IAM, but VPC Service Controls adds security cameras, motion sensors, and additional locks on individual rooms. Even if someone breaks through the front door, they still can't access your most valuable possessions. Throughout this presentation, I'll explain every single command in detail. When you see a G-Cloud command, I'll break down each parameter, explain why it's needed, show you what happens when you run it, and give you real-world context for when you'd use it. By the end, you'll be able to implement enterprise-grade data protection with confidence. We'll start with fundamental concepts, then progress through hands-on implementation, advanced enterprise patterns, troubleshooting, compliance, and automation. Each topic builds on the previous one, creating a complete foundation for VPC Service Controls Mastery. Understanding the security problem. Before we dive into the solution, let's understand the fundamental problem that VPC Service Controls solves. Traditional security models in the cloud, and frankly, in most IT environments, rely heavily on perimeter security and identity verification. Here's the scary reality. Once someone gets past your initial authentication, whether through stolen credentials, social engineering, or insider threats, they often have broad access to your systems. This diagram illustrates the stark difference between traditional security approaches and the modern, layered approach that VPC Service Controls enables. In the traditional model, authentication is like having a master key to your building. Once someone has that key, they can potentially access any room, any floor, any resource. This castle and moat approach worked when most threats came from outside the network, but today's threats are more sophisticated. Modern attackers often gain legitimate credentials through phishing, credential stuffing, or by compromising employees' personal accounts. Once they have valid credentials, traditional security systems can't distinguish between legitimate and malicious access. VPC Service Controls implements what security professionals call zero trust principles: never trust, always verify. Even with valid credentials, every access request is scrutinized based on multiple factors: location, device health, access patterns, time of day, and more. This multi-layered approach dramatically reduces the blast radius of security breaches. Even if credentials are compromised, attackers find themselves blocked by additional security checkpoints that legitimate users pass through seamlessly. VPC Service Controls core value proposition. Now let's dive into what VPC Service Controls actually does and why it's such a game changer for cloud security. At its core, VPC Service Controls creates invisible security boundaries around your Google Cloud services, but these boundaries are smart, they understand context. The first major benefit is data exfiltration protection. Even if an attacker compromises user credentials, they can't simply download your entire database to an external location. VPC Service Controls checks whether the access request is coming from an approved location, using an approved device, during approved hours. The second benefit is regulatory compliance. Many industries have strict requirements about where data can be processed and who can access it. GDPR requires that European citizen data stays within Europe. HIPAA mandates strict controls over healthcare data. VPC Service Controls helps you meet these requirements by enforcing geographic and access restrictions at the network level. The third benefit is context-aware access control. Traditional systems ask "Who are you?" VPC Service Controls asks "Who are you? Where are you? What device are you using?" What time is it? And does this access pattern match your normal behavior? This multi-factor approach catches threats that bypass traditional authentication. The real-world example I love to share. An employee's laptop gets stolen at a coffee shop. The thief has access to saved passwords and can even bypass two-factor authentication if the user was already logged in. With traditional security, this could be catastrophic. With VPC service controls, the system immediately notices that the same user credentials are now being used from a different geographic location, possibly on an unmanaged device, and blocks access to sensitive resources. This isn't theoretical. I've seen this exact scenario prevent real data breaches in production environments. Understanding the security request flow. This diagram shows exactly how security requests flow through Google Cloud when VPC service controls is implemented. Understanding this flow is crucial because it helps you troubleshoot issues and design effective security policies. When a user tries to access data, the request first hits Google Cloud's standard IAM identity and access management system. This is where traditional permission checking happens. Does this user have the storage? Objects.get permission on this bucket? If the user doesn't have the right IAM permissions, the request is denied immediately, just like in traditional Google Cloud security. But here's where VPC service controls adds its magic. If the IAM check passes, the request then goes through a second checkpoint, the VPC service controls evaluation. This is where the system asks those additional questions. Is this request coming from an approved network? Is the user accessing from a managed device? Does this access pattern match their normal behavior? Only if both checkpoints approve the request does the user actually gain access to the resource. This dual checkpoint approach means that even if someone compromises user credentials passing the IAM check, they still can't access data if they're coming from an unauthorized location or using an unmanaged device. The beauty of this system is that legitimate users rarely notice the additional security layer. If they're accessing data from their office computer during business hours, both checks pass seamlessly. But if someone tries to access the same data from an unexpected location or device, the second checkpoint blocks them. This flow also explains why VPC service controls is so effective against insider threats. Even employees with legitimate access can't exfiltrate data if they try to access it from personal devices or external locations that aren't approved by the security policies. The three fundamental building blocks. VPC service controls is built on three main components that work together like parts of a sophisticated security system. Understanding how these pieces fit together is absolutely crucial before we start building anything. The first component is service perimeters. Think of these as security zones or restricted areas within your Google Cloud environment. Just like a building might have different security zones, public lobby, employee areas, executive floor, server room, you create different perimeters for different types of data and applications. A typical enterprise might have perimeters for production customer data, development environments, shared services like logging and monitoring, and maybe special perimeters for highly sensitive data like financial records or personal information. The second component is access levels. These are the rules that determine who can enter each security zone. Access levels can be incredibly sophisticated. You might create one access level that says only from corporate office IPs addresses during business hours on managed devices with screen locks enabled. Another access level might say only from specific geographic regions for users who have completed security training in the last 90 days. The power is in the granularity and the ability to combine multiple conditions. The third component is protected services. These are the specific Google Cloud APIs that are subject to your perimeter restrictions. Not every Google Cloud service can be protected by VPC service controls, though the list grows regularly. Common protected services include cloud storage, where files are stored, BigQuery, for data analysis, Cloud SQL, managed databases, and Compute Engine, virtual machines. The architectural elegance comes from how these components interact. You create access levels once and reuse them across multiple perimeters. You define protected services globally and apply them selectively to different perimeters. This reusability makes management much easier as your security requirements become more complex. Component relationships and real examples. This table breaks down each component with concrete, real-world examples that you'll actually encounter in enterprise environments. Let me walk through each one to give you practical context. Service perimeters in practice might look like this. You create a production customer data perimeter that contains all projects handling live customer information. This perimeter has the strictest security controls. You might have a development and testing perimeter with more relaxed controls since it contains no real customer data. There might be a shared corporate services perimeter for things like centralized logging, monitoring, and backup systems that multiple teams need to access. Access levels become powerful when you think about your actual business requirements. A corporate network access level might require connections from your office IP ranges plus managed devices with current security patches. An executive access level might combine corporate network access with additional requirements like multi-factor authentication and approval workflows. An emergency access level might allow broader geographic access but require additional logging and approval processes. Protected services represent the actual Google Cloud APIs that store or process your sensitive data. When you specify StorageGoogleAPI.com as a protected service, you're saying that all cloud storage API calls within this perimeter must comply with the access levels. BigQuery GoogleAPI.com protects all BigQuery operations, data queries, dataset modifications, job submissions. SQL Admin GoogleAPI.com protects Cloud SQL database operations. The key insight is that access levels are reusable building blocks. You might create 5 different access levels representing different security requirements, then mix and match them across 10 different service perimeters. This creates a flexible, scalable security architecture that can grow with your organization. The relationship between these components also determines your troubleshooting approach. If users can't access data, you check. Are they in the right perimeter? Do they meet the access level requirements? Is the service they're trying to use actually protected by the perimeter? Enterprise Security Zone Architecture. This diagram represents a typical enterprise security architecture using VPC service controls. Let me walk you through each zone and explain why this design pattern works so well in real-world deployments. The production zone contains your most sensitive assets, such as customer databases, payment processing systems, and live application data. This zone has the strictest access controls, the most comprehensive logging, and the most restrictive network policies. In this diagram, it's colored red to indicate the highest security level. Only a small number of people have access to this zone, and that access is heavily monitored and logged. The development zone contains test databases, development applications, and staging environments. While still important, this zone can have more relaxed access controls since it doesn't contain real customer data. Developers need broader access here to do their work effectively, but you still want to prevent data exfiltration and maintain some level of security. This zone is colored yellow to indicate medium security. The shared services zone contains resources that multiple teams need to access, like centralized logging systems, security monitoring tools, backup systems, and maybe shared development resources like artifact repositories. This zone requires careful design because it needs to be accessible from other zones while maintaining security. The bridge perimeter is where the magic happens for inter-zone communication. This isn't a zone that contains resources directly. Instead, it creates controlled connections between other zones. In this example, development teams need access to shared logging services, but you don't want to give them broad access to the entire shared services zone. The bridge perimeter creates a secure tunnel that allows specific, controlled access. This architecture pattern scales beautifully. As your organization grows, you can add new zones for different business units, geographic regions, or compliance requirements. You can create additional bridge perimeters for specific cross-zone communication needs. The key is starting with a clear understanding of your data flows and security requirements, creating your first security system command deep dive. Now we get into the hands-on implementation. This slide shows the very first commands you will run to start building your VPC service control system. Let me explain each command in detail, including what happens when you run it and how to handle common issues. The first command, G-Cloud Access Context Manager Policies Create, establishes the top-level container for all your security settings. Think of this as creating the master control system for your building's security. Every other component, access levels, service perimeters, security policies, will belong to this access policy. The organization parameter is crucial and often confusing. You must use your organization's numeric ID, not the display name. If you do not know your organization ID, run G-Cloud Organizations List first. The output will show both the display name and the numeric ID. Use the numeric ID. It looks something like this. This parameter tells Google Cloud which organization this security policy belongs to. The title parameter is the human-readable name that will appear in the Google Cloud Console. Make this descriptive and meaningful to your team. I recommend including the environment, production, development, testing, and the purpose. Good examples: Production Customer Data Security Policy or Development Environment Access Controls. The member parameter grants administrative access to this policy. This person can create and modify access levels, service perimeters, and other security settings. In production environments, I strongly recommend using a Google group instead of individual users. This makes it easier to manage permissions as your team changes. When you run this command successfully, Google Cloud returns a policy ID. This is absolutely critical to save. You will need this policy ID for every subsequent command. I recommend documenting it in your team's knowledge base immediately. The remaining commands show you how to verify and explore your new policy. The list command shows all policies in your organization, and the describe command gives you detailed information about a specific policy. Command parameter deep dive and troubleshooting. Let me break down exactly what each part of that access policy creation command is, because understanding these details will save you hours of troubleshooting later. The G-Cloud prefix is your command line interface to Google Cloud. It's like saying, "Hey Google Cloud, I want to run a command." The Access Context Manager part specifies that this command relates to VPC service controls functionality. Google Cloud organizes commands into logical groups, and Access Context Manager is the group for all VPC service controls operations. The policies create subcommand tells Google Cloud exactly what type of resource you want to create. In the Access Context Manager command group, you can create policies, access levels, service perimeters, and other components. Each has its own create subcommand. The organization parameter deserves special attention because it's a frequent source of errors. When you run G-Cloud Organizations List, you'll see output like this: display_name, my company Inc. and ID. Always use the ID number, never the display name. The display name can change, but the ID is permanent. The title parameter is purely for human consumption. It doesn't affect functionality, but it's what you'll see in the Google Cloud Console. Make it clear and descriptive because you'll be looking at it often. The member parameter uses Google Cloud's standard identity format. For individual users, user, email@domain.com. For Google Groups, group, group name@domain.com. For service accounts, service account, name@project.iam.gserviceaccount.com. In production, always use groups for easier management. Common error scenarios. If you get organization not found, double-check that you're using the numeric organization ID, not the display name. If you get permission denied, make sure you have the organization policy administrator role or similar permissions. If the command hangs, check your network connection and authentication status with G-Cloud Auth List. When the command succeeds, you'll see output like created policy. That number is your policy ID. Write it down immediately. You'll use it in every subsequent VPC service controls command. Access rules creation. Complete command analysis. These commands create the access rules that determine who can enter your security zones and under what conditions. Let me walk through each command in detail, explaining every parameter and showing you how to customize them for your specific needs. The first command creates a basic access level with network and geographic restrictions using the command G Cloud Access Context Manager levels create corporate_network. Here, corporate_network is the name you will use to reference this access level in other commands. Choose descriptive names that make sense to your team. The parameter policy connects this access level to the policy we created earlier. Every access level must belong to a specific policy. Replace the number with the actual policy ID you got from the previous command. The parameter title is the friendly name that appears in the Google Cloud Console. This should clearly describe what this access level represents. Now for the access conditions. The parameter basic level I subnetwork specifies which IP address ranges are allowed. These are RFC 1918 private address ranges commonly used in corporate networks. You will need to replace these with your actual office network ranges. You can specify multiple ranges separated by commas. The parameter basic level regions restricts access to specific countries using ISO country codes, such as US and CA. This is crucial for compliance with data residency requirements. If your organization operates globally, you might include more countries, but be thoughtful about this, it is a security control. The second command creates a device-based access level. The parameter basic level device policy sets device security requirements, such as require screen lock true and require admin approval false. Require screen lock true means users must have screen locks enabled on their devices. Require admin approval false means devices do not need explicit admin approval, but you could set this to true for higher security environments. The third command creates a composite access level using the parameter basic level required access levels, specifying corporate_network and managed_devices. This creates in logic, meaning users must satisfy both the corporate_network access level and the managed_devices access level to gain access. This is powerful for creating layered security requirements. The final command lists all access levels in your policy, which is useful for verification and documentation. Building your first service perimeter. Now we're going to create our first service perimeter. Think of this as building the actual secure zone where your data lives. This is where VPC service controls gets really powerful, because you're defining exactly which Google Cloud projects contain sensitive data and need protection. The command starts with G Cloud Access Context Manager perimeters create customer data zone. Here, customer data zone is the name you'll use to reference this perimeter in other commands. Choose names that clearly describe what's inside, like customer data zone, financial systems, or development environment. The policy parameter connects this perimeter to the access policy we created earlier. Every perimeter must belong to a specific policy, and you'll use the policy ID you saved from slide 8. The title parameter is the human-friendly name that appears in the Google Cloud Console. Make this descriptive because your security team will see this name when reviewing access logs and security reports. The resources parameter is crucial. This defines exactly which Google Cloud projects are inside this security zone. You specify projects by their numeric ID, not their display names. You can include multiple projects separated by commas. These projects will be subject to all the access restrictions defined by this perimeter. The restricted services parameter specifies which Google Cloud APIs are subject to perimeter restrictions. When you include storage.googleapi.com, all cloud storage operations in these projects require users to meet the access level requirements. Including BigQuery.googleapi.com means all BigQuery operations, running queries, accessing datasets, managing jobs, are also protected. The access levels parameter connects the access rules we created earlier to this perimeter. Users must satisfy both access levels to access protected services in this perimeter. This creates layered security where users need to be on the corporate network and using managed devices. The second command shows you how to verify your perimeter was created correctly, and the third command demonstrates how to get detailed information about the perimeter, including all its settings and which projects it protects. Understanding service perimeter configuration details. Let me break down each parameter in that service perimeter creation command, because understanding these details is critical for troubleshooting and customizing your security setup. The perimeter name, customer data zone in our example, becomes part of the resource identifier. Google Cloud creates a full resource name like access policies, service perimeters, customer data zone. You'll use this full name in some advanced commands, but usually just the short name works. When specifying projects in the resources parameter, you must use project numbers, not project IDs or display names. Project numbers are immutable. They never change even if you rename the project. To find project numbers, run G-Cloud Projects List Format Table Project Number, Project ID, Name. The project number column gives you the values to use. The restricted services list is where you define which Google Cloud APIs are subject to perimeter controls. Not every Google Cloud service supports VPC service controls. Understanding protected services and their impact. Here are the most commonly used protected services and what happens when you include them in a perimeter. Understanding this is crucial because different services have different implications for your users and applications. When you protect storage.googleapi.com, you are controlling all cloud storage operations, uploading files, downloading files, listing buckets, and managing bucket permissions. This is often the first service organizations protect because cloud storage frequently contains sensitive data like database backups, customer files, and application logs. Protecting BigQuery.googleapi.com affects all BigQuery operations, running SQL queries, accessing datasets, creating tables, and managing BigQuery jobs. This is critical for organizations using BigQuery for data analytics, because BigQuery often contains aggregated customer data, financial information, and business intelligence data. Including SQLadmin.googleapi.com protects cloud SQL database operations, but it is important to understand this affects database administration, not the actual SQL queries your applications run. Your applications will still work normally, but DBIs will not be able to create new databases or modify database configurations unless they meet the access level requirements. Compute engine protection through compute.googleapi.com is complex because it affects virtual machine management operations, creating virtual machines, modifying virtual machines, accessing virtual machine metadata, and managing instance groups. However, it does not affect applications running on those virtual machines or network traffic between virtual machines. The key insight is that VPC service controls protects Google Cloud API calls, not the actual data flow between your applications. Your web application can still serve customers normally, but if someone tries to download the database backup from cloud storage using an unapproved device, they will be blocked. Container registry and artifact registry protection is particularly important for development teams. These services store your Docker images and application packages. Protecting them ensures that only authorized developers can deploy new application versions, which is crucial for preventing supply chain attacks. Creating multiple perimeters for different security needs. Real enterprises need multiple security zones with different access requirements. This slide shows you how to create a complete multi-zone security architecture that matches how businesses actually operate. The first perimeter is for production customer data. This gets the highest security level. Notice that it requires 3 access levels. Corporate network, referring to office locations, managed devices, meaning company-controlled computers, and executive access for additional approval requirements. This creates a very restrictive environment where only a small number of people can access customer data, and only under controlled conditions. The second perimeter is for development and testing environments. This has more relaxed security, only requiring corporate network access. Developers need flexibility to experiment and test, but you still want to prevent unauthorized access from external locations. This perimeter might contain test databases, development applications, and staging environments. The third perimeter creates shared services that multiple teams need to access. This includes centralized logging, monitoring systems, and backup services. The access requirements are moderate, corporate network plus managed devices, but not executive access. This reflects the fact that many people need access to logs and monitoring, but you still want to control who can access these systems. The bridge perimeter is the most sophisticated concept. It allows controlled communication between different security zones. In this example, development teams need access to centralized logging services, but you don't want to give them broad access to the entire shared services zone. The bridge perimeter creates a secure tunnel that allows specific, controlled access. Notice how the bridge perimeter works. It includes projects from both the development zone, projects 789, 790, and the shared services zone, project 222. It specifies ingress and egress rules that define exactly which services can communicate across zone boundaries. This is like having a security checkpoint between different floors of a building. Authorized people can pass through, but only for specific, approved purposes. The naming convention is important here. Use descriptive names that indicate both the purpose and security level. Prod customer data clearly indicates production level customer data, while dev testing indicates development level access. This makes it much easier to manage as your system grows. This multi-perimeter approach scales beautifully. You can add new perimeters for different business units, geographic regions, or compliance requirements. Each perimeter can have its own access requirements tailored to the specific security needs of the data it protects. Advanced perimeter features, ingress and egress rules. This slide introduces the most sophisticated feature of VPC service controls, ingress and egress rules. These rules control data flow into and out of your perimeters, which is essential for preventing data exfiltration while still allowing legitimate business operations. Ingress rules control who can access resources inside the perimeter from outside locations. The example shows an ingress rule that allows the backup service, running on the service account identity backup service at backup project, to access cloud storage APIs within the perimeter. This is crucial for automated backup systems that need to copy data to external backup locations. The ingress rule specifies several key components. The from section defines the identity that's requesting access, in this case, a service account. The to section specifies which operations are allowed. Here, it's storage.googleapi.com operations, meaning this backup service can read and write cloud storage data but can't access BigQuery or other protected services. Egress rules control data flowing out of the perimeter to external services. The example shows an egress rule allowing access to an external logging service. This is common in enterprise environments where centralized logging systems run outside the main security perimeter but need to collect logs from protected systems. The egress rule structure is similar but reversed. The from section specifies which identities inside the perimeter can make external requests. Here, the logging service account. The to section defines the external destination, in this case, a specific external project that hosts the logging infrastructure. These rules solve a critical challenge in cloud security. How do you protect sensitive data while still allowing necessary business processes to function? Without ingress and egress rules, you'd have to choose between security and functionality. With them, you can have both. The real power comes from the granularity. You can create ingress rules that allow specific service accounts to access specific APIs at specific times. You can create egress rules that allow data to flow to specific external services but nowhere else. This creates a very precise security model that matches your actual business needs. Common use cases for ingress rules include backup services, monitoring systems that need to collect metrics, and CI/CD pipelines that deploy applications to production. Common egress use cases include logging to external services, API calls to third-party services, and data exports for business intelligence. Bridge perimeters. Connecting security zones safely. Bridge perimeters are one of the most powerful but least understood features of VPC service controls. They solve a common enterprise challenge. How do you allow controlled communication between different security zones without compromising the security of either zone? This diagram shows a typical enterprise scenario. You have a high security production zone containing customer data, a medium security development zone for testing, and a shared services zone containing logging and monitoring tools. Without bridge perimeters, you'd have to choose between isolation, meaning development teams can't access logs, or openness, meaning development teams get broad access to shared services. The bridge perimeter creates a secure tunnel between zones. In this example, development projects need access to centralized logging services, but you don't want to give developers broad access to all shared services. The bridge perimeter includes specific projects from both zones and defines exactly which services can communicate across the boundary. The technical implementation is elegant. The bridge perimeter contains Project 789 from the development zone and Project 333 from the shared services zone. It allows logging.googleapi.com API calls to flow between these specific projects but blocks everything else. This means developers can view logs related to their applications but can't access backup systems, security monitoring, or other shared services. The access level for the bridge perimeter can be different from either connected zone. In this example, the bridge requires corporate network access. This means that even though the development zone might allow broader access, communication through the bridge requires users to be on the corporate network. Testing your perimeter configuration. Testing is absolutely critical when implementing VPC's service controls because misconfigured perimeters can block legitimate users while still allowing unauthorized access. This slide shows you a systematic approach to testing that will catch configuration errors before they impact your users. The first test uses the dry run capability. The G-Cloud Alpha Access Context Manager Perimeters Dry Run command shows you exactly what would happen if a specific user tried to access specific resources, without actually blocking anything. This is incredibly valuable for validating your configuration before enforcing it. In the dry run example, we are testing whether user Alice can access BigQuery in project. The command simulates the access request and shows you whether it would be allowed or denied, along with detailed reasoning. This helps you understand exactly how your access levels and perimeter rules interact. The second test script shows you how to test from different access contexts: corporate network, external network, managed device, and unmanaged device. This systematic testing approach ensures that your perimeters work correctly in all scenarios. You should test with real user accounts and real devices, not just theoretical scenarios. The testing process should include positive tests, ensuring authorized users can access resources, and negative tests, ensuring unauthorized users are blocked. Many organizations focus only on negative testing, then discover that their perimeters also block legitimate users. Common implementation pitfalls and how to avoid them. After implementing VPC service controls in dozens of organizations, I've seen the same mistakes repeated over and over. This slide covers the most common pitfalls and how to avoid them, potentially saving you weeks of troubleshooting and user frustration. The first major pitfall is starting with production data. Many teams want to jump straight to protecting their most sensitive assets, which seems logical but creates huge risks. If you misconfigure VPC service controls on production systems, you might accidentally block critical business processes or prevent applications from accessing necessary resources. Always start with development or test environments where mistakes won't impact customers. The second pitfall is not considering service accounts. Many organizations focus on human users but forget about the automated systems that access their data. Service accounts for backup systems, monitoring tools, CI/CD pipelines, and automated reports all need to be considered in your access level design. If you forget about these, automated systems will start failing mysteriously after you implement perimeters. The third pitfall is forgetting about mobile access. Many access level configurations work perfectly for desktop users in the office but break completely for employees using mobile devices or working from home. Mobile devices often don't support all the device management features that desktop computers do, and mobile IP addresses can change frequently. The timing pitfall catches many teams off guard. VPC service controls changes can take 5 to 10 minutes to propagate across Google Cloud's global infrastructure. Teams often make a change, test immediately, see that nothing happened, and assume the configuration is wrong. Then they make additional changes that compound the problem. Always wait at least 10 minutes before concluding that a change didn't work. The access level logic pitfall is particularly tricky. When you specify multiple access levels for a perimeter, they create an AND condition. Users must satisfy all access levels. Many teams expect OR logic and are surprised when users who meet some but not all requirements are still blocked. The geographic restrictions pitfall affects global organizations. If you restrict access to specific countries, make sure you consider traveling employees, distributed teams, and cloud infrastructure that might be located in different geographic regions than your users. The gradual rollout approach I recommend. Start with a single development project. Test thoroughly with multiple user types and access scenarios. Gradually expand to more projects. And only protect production systems after you're confident in your configuration. Advanced Device Policy Configuration. Device policies are where VPC service controls gets really sophisticated. Instead of just checking is this a managed device, you can create detailed requirements about device security posture, encryption status, and compliance policies. This slide shows you how to implement enterprise-grade device security requirements. The first command shows a comprehensive device policy with multiple security requirements. Require screen lock equals true ensures that devices have screen locks enabled. This prevents unauthorized access if a device is lost or stolen. Require admin approval equals true means that each device must be explicitly approved by an administrator before it can access protected resources. The allowed encryption statuses equals encrypted parameter is crucial for organizations handling sensitive data. This requirement ensures that device storage is encrypted, protecting data even if the physical device is compromised. Most modern corporate devices support encryption, but this policy enforces it as a requirement rather than leaving it optional. The allowed device management levels equals managed parameter ensures that only devices under corporate management can access protected resources. Managed devices are enrolled in your organization's device management system, like Google Workspace Device Management or Microsoft Intune, giving administrators control over security policies, app installation, and device configuration. The second command demonstrates how to create different device policies for different security needs. An executive access policy might require additional security features like remote wipe capability and mandatory VPN connections. A contractor access policy might allow less stringent requirements while still maintaining basic security standards. The mobile device considerations are particularly important. The third command shows a mobile-specific policy that accounts for the unique characteristics of phones and tablets. Mobile devices often have different encryption capabilities, different management options, and different user behavior patterns. You might allow personal mobile devices for some access but require corporate-managed mobile devices for sensitive operations. Device policies also interact with other security tools in interesting ways. If your organization uses certificate-based authentication, you can require specific certificates to be installed on devices. If you use VPN technologies, You can require active VPN connections for certain types of access. The testing approach for device policies should include real devices in various states, freshly enrolled corporate devices, older devices with different operating system versions, and devices that might not meet all requirements. This testing helps you understand how your policies will affect real users in real scenarios. Geographic and time-based access controls. Geographic and time-based controls add another powerful layer to your security architecture. These controls are particularly important for compliance with data residency requirements and for preventing access during unusual hours when security teams aren't actively monitoring. The first command shows how to implement geographic restrictions using ISO country codes. The basic level regions parameter restricts access to users physically located in the United States, Canada, and Great Britain. This is crucial for compliance with regulations like GDPR, which requires that European citizen data be processed within European borders. Geographic controls work by examining the source IP address of access requests and mapping them to geographic locations. However, this isn't perfect. VPNs and proxy servers can make users appear to be in different locations than they actually are. Most organizations combine geographic controls with other access requirements to create layered security. The second command demonstrates time-based access controls. The time windows are specified in JSON format with day of week and hour ranges. In this example, access is allowed Monday through Friday from 6 a.m. to 8 p.m. Pacific Time. This prevents unauthorized access during nights and weekends when security teams might not be actively monitoring. Time-based controls are particularly effective against automated attacks, which often occur during off hours to avoid detection. They're also useful for compliance scenarios where regulations require that data access be restricted to business hours. The combination example shows how to create sophisticated access requirements that include multiple factors. Users must be in approved countries, accessing during business hours, using managed devices, and connecting from corporate networks. This creates a very high security bar that's appropriate for the most sensitive data. When implementing geographic controls, consider your actual business needs carefully. If you have remote employees, traveling employees, or business operations in multiple countries, overly restrictive geographic controls can significantly impact productivity. Start with broader geographic allowances and gradually tighten them as you understand your actual usage patterns. Time-based controls should account for different time zones if your organization operates globally. You might need separate access levels for different regions, or you might need to allow broader time windows to accommodate global operations. Both geographic and time-based controls can be overridden by emergency access procedures, which we'll cover in later slides. This ensures that critical business operations can continue even when normal access controls would prevent them. Troubleshooting VPC's service controls issues. When VPC's service controls blocks legitimate users, the debugging process can be complex because multiple layers of security are interacting. This slide provides a systematic troubleshooting approach that will help you quickly identify and resolve access issues. The first command, G-Cloud Logging Read, searches for VPC's service controls violation entries in your audit logs. The filter specifically looks for VPC's service controls violation entries, which are generated whenever someone is blocked by your perimeter rules. These logs contain detailed information about what was blocked and why. The timestamp filter limits results to the last hour, which is usually sufficient for investigating immediate issues. You can adjust this timeframe based on when the problem occurred. The logs will show you the user identity, source IP address, requested resource, and specific access level that failed. The second command checks a specific user's access levels. This is incredibly useful when users report they can't access resources. You replace alice@company.com with the actual user's email address, and the command shows you which access levels they currently satisfy. Common issues include users not being on managed devices, accessing from unapproved locations, or trying to access during restricted time windows. The third diagnostic command simulates an access request without actually performing it. This dry run capability lets you test whether a specific user would be able to access a specific resource with their current access context. It's like having a what-if simulator for your security policies. The fourth command lists all current perimeter configurations, which is essential for verifying that your security rules are configured as expected. Sometimes access issues are caused by recent configuration changes that had unintended consequences. The troubleshooting decision tree helps you systematically narrow down the problem. Start by checking if the user has basic IAM permissions. VPC's service controls adds an additional layer on top of IAM, but users still need underlying permissions. Then verify their access levels, check perimeter membership, and finally examine any ingress/egress rules that might affect their access. Common resolution patterns include adding users to appropriate access levels, updating perimeter configurations to include forgotten projects or services, and creating ingress rules for legitimate automated systems that were accidentally blocked. Real-world troubleshooting scenarios. Let me walk you through the most common troubleshooting scenarios I encounter in production environments. Understanding these patterns will help you resolve issues quickly when they arise in your organization. The user can't access from home scenario is extremely common, especially with remote work. The user has the right IAM permissions and is using a managed device, but they're being blocked because they're accessing from a residential IP address that's not in your corporate IP ranges. The solution involves either expanding your access levels to include VPN IP ranges or requiring users to connect through a corporate VPN first. The automated backup failed scenario reveals a critical aspect of VPC service controls. Service accounts are subject to the same restrictions as human users. Your backup service account needs to meet access level requirements just like any user. The solution typically involves creating a specific access level for service accounts or adding ingress rules that allow the backup service to access protected resources. The mobile app stopped working scenario highlights the complexity of mobile device management. Mobile devices often can't meet the same security requirements as desktop computers. They might not support certain encryption standards or device management features. The solution usually involves creating separate, mobile-friendly access levels with relaxed device requirements while maintaining other security controls. The CI/CD pipeline broken scenario is particularly challenging because build systems often run on shared infrastructure that doesn't meet typical corporate device requirements. Build servers might not be managed devices in the traditional sense, and they might be hosted in data centers with IP addresses that aren't in corporate ranges. Solutions include creating specific access levels for build infrastructure or using service account keys with ingress rules. The third-party integration failed scenario occurs when external partners or vendors need access to specific resources. These systems obviously can't meet your corporate device requirements, and they're accessing from external IP addresses. The solution involves carefully crafted ingress rules that allow specific external service accounts to access specific resources while maintaining overall security. For each scenario, I've included the diagnostic steps to identify the root cause and the specific commands to implement the solution. The key is systematic debugging. Don't guess at solutions. Use the logging and diagnostic tools to understand exactly why access is being blocked. Setting up comprehensive monitoring and alerting. Monitoring VPC service controls is crucial for both security and operational purposes. You need to know when legitimate users are being blocked, when security violations are occurring, and when your access patterns change in ways that might indicate security threats. The first monitoring command creates a log sync that exports all VPC service controls events to BigQuery for analysis. This gives you a centralized location to analyze access patterns, identify trends, and create reports for security audits. The BigQuery dataset becomes your historical record of all security-related access events. The cloud monitoring metric tracks the rate of VPC service controls violations in real time. This metric shows you when violations are occurring and helps you identify patterns. For example, If violations spike during certain hours, it might indicate legitimate users having trouble with time-based restrictions rather than actual security threats. The alerting policy automatically notifies your security team when VPC service controls violations exceed normal thresholds. The threshold of 5 violations in 5 minutes is a starting point. You should adjust this based on your organization's normal patterns. Too low, and you'll get false alarms from legitimate configuration issues. Too high, and you might miss actual security incidents. The dashboard creation gives your security team a visual interface for monitoring VPC service controls activity. Good dashboards include violation rates over time, top violated resources, geographic distribution of access attempts, and trends in access level failures. This visual representation helps security teams quickly identify patterns that might be missed in raw log files. The custom log-based metrics let you track specific patterns that are important to your organization. You might create metrics for failed access attempts from specific geographic regions, violations of specific access levels, or attempts to access particularly sensitive resources. These custom metrics can feed into more sophisticated alerting and analysis systems. I particularly recommend setting up separate monitoring for different types of access. Human users, service accounts, and external integrations often have different normal patterns, and combining them can mask important signals in the noise. The monitoring setup should also include regular reviews of access patterns. Monthly or quarterly reviews help you identify access levels that might be too restrictive, causing operational problems, or too permissive, reducing security effectiveness. Emergency access procedures and break glass scenarios. Every VPC service controls implementation needs emergency access procedures for critical situations where normal security controls might prevent necessary business operations. This slide shows you how to implement these procedures safely while maintaining audit trails and preventing abuse. The emergency access level is designed for true emergencies, major system outages, security incidents, or business-critical situations where normal access procedures would cause unacceptable delays. Notice that this access level is much more permissive than normal levels, but it's still not completely open. It requires managed devices and has geographic restrictions to prevent abuse. The emergency perimeter temporarily relaxes restrictions on critical systems while maintaining basic security controls. This perimeter should only be activated during declared emergencies and should automatically expire after a short period. The temporary flag in newer G Cloud versions can automatically disable the perimeter after a specified time. The activation procedure requires multiple approvals to prevent abuse. The two-person authorization pattern means that one person can't unilaterally disable security controls. Both the security team lead and a business executive must approve emergency access activation. This creates accountability and ensures that emergency procedures are only used for legitimate emergencies. The logging enhancement during emergency access is crucial. You want detailed logs of all activities that occur under emergency access so you can review them after the emergency is resolved. The enhanced logging captures not just what was accessed, but who accessed it, when, and from where. The automatic expiration procedure ensures that emergency access doesn't accidentally remain enabled after the emergency is resolved. The procedure includes automated reminders to the security team and automatic disabling of emergency access after 24 hours unless explicitly extended. Documentation is critical for emergency procedures. The emergency access playbook should include step-by-step instructions for activation, clear criteria for when emergency access is appropriate, and detailed procedures for post-emergency review. This documentation should be accessible even if normal IT systems are down. Compliance and audit reporting. VPC service controls generates extensive audit logs that are crucial for compliance with regulations like GDPR, HEPA, SOX, and PCI DSS. This slide shows you how to extract and present this information in formats that auditors and compliance teams need. The BigQuery compliance query extracts comprehensive access information including user identities, source locations, accessed resources, and timestamps. This query structure matches the information requirements for most compliance frameworks. The geographic information is particularly important for GDPR compliance, which requires organizations to track where European citizen data is accessed. The access report generation creates formatted reports that auditors can easily review. These reports typically need to show who accessed what data, when they accessed it, whether the access was authorized, and what controls were in place during the access. The reports should be generated regularly, monthly for most organizations, weekly for high-security environments. The security control validation demonstrates to auditors that your VPC service controls are actually enforcing the policies you've documented. The validation includes testing that unauthorized access is blocked, that access levels work as designed, and that emergency procedures have appropriate controls and audit trails. Compliance framework mapping. Different compliance frameworks have specific requirements that VPC service controls can help you meet. This table maps common compliance requirements to specific VPC service controls features, helping you understand how to configure your security controls to meet regulatory obligations. GDPR Article 32 requires appropriate technical and organizational measures to protect personal data. VPC Service Controls directly supports this by providing technical controls that restrict data access based on location, device security, and user authorization. The geographic restrictions ensure that European citizen data stays within approved regions, while device controls ensure that data is only accessible from secure, managed devices. HEPA's administrative safeguards require assigned security responsibilities and access management. VPC Service Controls supports this through role-based access controls and detailed audit logging that shows who accessed what patient data and when. The access level requirements ensure that only authorized personnel with appropriate device security can access healthcare data. Infrastructure as code with Terraform. Managing VPC service controls through infrastructure as code ensures consistency, enables version control, and allows you to apply software development best practices to your security configuration. This slide shows you how to implement VPC service controls using Terraform. The Terraform configuration starts by defining the access policy resource, which is the top-level container for all VPC service controls components. Notice how we're using Terraform variables for the organization ID and administrator email. This makes the configuration reusable across different environments and organizations. The access level resource definitions show how to create the same access levels we built manually earlier, but now they're defined in code. This means you can version control your security policies, review changes through pull requests, and automatically apply consistent security configurations across multiple environments. Automated deployment and GitOps workflows. This slide shows you how to implement continuous deployment for VPC service controls using cloud build and GitOps principles. This approach ensures that security configuration changes are tested, reviewed, and deployed consistently across environments. The cloud build configuration implements a complete CI/CD pipeline for VPC service controls. When changes are pushed to your configuration repository, Cloud Build automatically validates the Terraform configuration, runs security checks, and applies changes to appropriate environments based on the branch that was updated. The validation step runs Terraform plan to show exactly what changes would be made without actually applying them. This plan output is saved as a build artifact and can be reviewed by security teams before changes are applied. The validation also includes custom security checks that verify the configuration meets your organization's security standards. The environment-based deployment logic applies changes to development environments automatically when changes are pushed to the main branch, but requires manual approval for production deployments. This gives you confidence that changes work correctly in development before they affect production systems. The approval process integrates with your existing code review workflows. Security configuration changes require approval from both security team members and infrastructure teams, ensuring that changes are reviewed from both security and operational perspectives. Performance impact and optimization. VPC service controls adds security layers that can impact application performance if not implemented thoughtfully. This slide shows you how to measure, monitor, and optimize the performance impact of your security controls. The performance monitoring setup tracks key metrics that indicate how VPC service controls affects your applications. Latency monitoring shows whether security checks are adding significant delays to API's calls. Error rate monitoring helps you distinguish between application errors and security-related blocks. Throughput monitoring shows whether security controls are limiting the rate at which your applications can process requests. The optimization techniques help you minimize performance impact while maintaining security. Caching access level evaluations reduces repeated security checks for the same user and resource combinations. Regional optimization places security evaluation logic closer to your users and applications, reducing network latency. Connection pooling reduces the overhead of establishing secure connections for each API call. Advanced shared VPC scenarios. Shared VPC architectures require special consideration when implementing VPC service controls. This is because network resources are shared across multiple projects, while security boundaries need to be maintained at the project level. This slide shows you how to implement VPC service controls effectively in complex shared VPC environments. In a shared VPC setup, you typically have a host project that contains the network infrastructure, such as VPCs, subnets, and firewalls, and multiple service projects that contain applications and data. VPC service controls perimeters need to be designed to respect this architecture while providing appropriate security boundaries. The host project perimeter usually contains the shared VPC host project and has access levels that allow network administrators to manage the shared infrastructure. This perimeter typically protects compute engine APIs, used for managing network resources, and might include specific ingress rules for network monitoring and management tools. Service project perimeters contain the individual application projects that use the shared VPC network. Each service project can have its own perimeter with appropriate access levels for that application's security requirements. Zero Trust architecture with VPC service controls. Zero Trust is a security philosophy that assumes no implicit trust based on network location, device ownership, or user credentials alone. Every access request must be verified before granting access to resources. VPC service controls is perfectly positioned to implement zero trust principles in Google Cloud environments. The traditional security model relies on network perimeters. If you're inside the corporate network, you're trusted. Zero Trust eliminates this assumption. Instead, every request is evaluated based on multiple factors: who is making the request, what device they're using, where they're located, what they're trying to access, and whether this access pattern is normal for this user. VPC service controls implements zero trust through its layered evaluation system. First, it verifies user identity through IAM, then it checks device security posture. Is the device managed, encrypted, and up to date? Next, it evaluates network location. Is the request coming from an approved location or VPN? It also considers time factors. Is this access happening during normal business hours? The contextual access level in the example shows how to implement sophisticated zero trust policies. This access level requires multiple conditions to be satisfied simultaneously. The user must be on a managed device, accessing from an approved location, during business hours, and the device must meet specific security requirements. Continuous verification is a key zero trust principle. Traditional security systems grant access once and trust that access until the session expires. Zero Trust continuously evaluates access throughout the session. If conditions change, for example, if a user moves to an untrusted network during their session, access can be immediately revoked. The behavioral analysis integration shows how VPC service controls can work with Google Cloud Security Analytics to detect unusual access patterns. If a user suddenly starts accessing resources they've never accessed before, from a location they've never used, at an unusual time, the system can require additional verification or block access entirely.